Talking and then several people got 100 on the test. The low is really low, 29. The median is 81. I was expecting slightly higher than that, but let's see. Homework number, what are we now on? 5 is due on Wednesday, right? And then we're gonna have a quiz on chapter 4 on Monday, March 4th. And then we're going to have our test 2. Our test 2 is coming up pretty quickly. Test 2 is going to be, when's our test 2? Wednesdays, I think it's on a Monday. Let's see. Yeah, because I have to leave for the airport on a Wednesday. So this is this circuit? No, this is not circuit. So, because we only have 2 chapters on the next test, and we're almost done. Yeah. Where's our calendar? Right here. It doesn't say when our test is. Huh? It's not showing. Yes. So let's see what's on. It's probably, I think it's this one here. That's, oh no. March, I have a feeling that it's this one is our test. Yeah. It's March 18th. So it's on a Monday. Monday. So it's 3 weeks from today, right? Okay, it's not that soon. Okay. Questions on the homework that's due Wednesday? Number 11. Oops, I need to share my desktop, and I'm recording, right? I'm recording, but I'm not checking my desktop. Okay. I am sharing my desktop. Then I'm looking at homework number 5. Number, which one? I talked about this last night. Someone asked about this problem last night. So it's recorded on the, okay? Any other questions on the homework? Oh, someone asked a question. Number 15, he's saying. Number 15. So this one is by superposition. So you expect how many parts to your solution? There's 3 parts because you have 3 independent sources, right? Okay. So the first part would be, we can say that it's when the 20-volt source is on. Okay. So what do I do with the 2 amp source? What do I do when I'm looking at the contribution of the 2-volt source? What do I do with the 2 amp source? Are you sure? Open it. It's a current source, and then the 16 volts you short, right? So what do I do now to find I? You can use any method you want to find I. Any suggestions? Mesh, no. How about 20 volts? So this one is gone. It's an open circuit. I can just use find the total current in this current divider, maybe, because this 1 and 3 are now in series. That becomes a 4. Everyone okay with that? And it's parallel with a 4, right? So what is the total current that goes this way? So the total resistance is 4 parallel with a 4 is a 2, right? 4 parallel with a 4 is a 2. Everyone okay with that? And it's actually in series with the remaining 2. So the total current through the voltage source would just be 20 volts divided by 2 plus 2 ohms, which is 5 amps. Everyone okay with that? Once I have the 5 amps, I can find the current that I'm looking for. It's actually a nice evenly divided current because it's 4 and 4. So the I contribution would just be half of that, which is 2.5. Did you follow what I did? Instead of using nodal or mesh, I just simplified the resistors. This 1 ohm and this 3 ohms are now in series because this is out of the picture. It's an open. So that 4 is now in parallel with the 4, combined together into a 2, which is in series with the 2. Therefore, the total current will be 20 divided by 2 plus 2, which is 5. And then what do I do with the 5? So there's a 5 amp total current here. It's being divided evenly between the 4 ohms on the left and the 4 ohms on the right. So it's going to be 2.5. Okay? Did you see that email about NSF scholarships? Okay. What did it say? Reimbursement? Oh, because somebody got in trouble. You want to test? Okay. Then the next part would be when, which one do you want to look at now? When the two amp source is on. Okay, what do I do with a 20 volt source? What do I do with this? Short. With a smile on his face. How about the 16 volt source? Short. Okay, I count everyone that. Every time you say that. Okay, so what do I do now in order to find I? Any suggestions? So, do you agree that the 2 and the 4 are in, what's the relationship between the 2 and the 4? They're in parallel, right? Some of you will probably do mesh all the time, that's fine, but let's try and simplify. The 2 and the 4 are in parallel, do you agree? They are connected to the same 2 nodes, the top node and the bottom node. So what's 2 parallel to a 4? It's 8, okay, 4/3, okay? And how is that 4/3 related to the rest of the circuit? The 4/3 now is in what? Is in series with the 3, right? With this 3, okay? Because these 2 got replaced by a single one, right? Of 4/3, and the 4/3 and the 3 are now in series. Okay, so what that becomes what? 3 plus 4/3 would be 10/3. Oh, no. 9 plus 4 is 13/3, right? Yes. Okay, and that 13/3 is now in parallel with the 1. Yes, with a 1. Because I combined these 2 into one resistor. This is now in parallel with the 1. So now I can use current divider. So if I use current divider, what's I now? It's going to be the G of the 13/3. So it's going to be 3 over 13 divided by 3 over 13 plus the G of the 1, which is 1 over 1 multiplied by the total current of 2. Do you understand how I did the current divider equation here? Okay, so I redrew it like this. Here's the 2 amps. Okay, okay. Here's the 1, right? Okay, and the other three, the other two, the 13/3 is like this. Yes? Hmm? All the three elements are now in just parallel, right? That's why I'm using the current divider equation. Okay? And then finally, what do you do next? The 16-volt source, right? As you can see, the what do you call this? Superposition is a nice idea, right? But it doesn't always simplify your solution, right? Instead of having to do it only by nodal or mesh one time, you actually have to do the problem 3 times, right? Okay, so the last part is when the 16 volts is on.
So, sorry, that 4 ohm resistor all the way on the right.
What?
4 ohm resistor all the way on the right.
This one, or yes.
This one parallel to 2 all the way on the left.
Correct. That's why we get the 4/3.
Got it.
Because we shorted the 2 voltage sources. Okay. We replaced the voltage sources with wires. How's that? Smart, huh? Okay. When the 16 volts is on, what do I do with the 20? Oh, why did I ask that? Replace with a wire. What do I do with the 2 amps? Open circuit. Okay. So how do we find the I? Oh, so this one you have to be careful, right? The I that the 16 volt source is going to generate is actually opposite the I as they labeled it. So you expect a negative value. So what do we do? The 1 and the, oops, I covered it. What's that number here? 1 and the 3 are in series, right? So this 2 will become a 4, right? And the 2 and the 4 are in parallel. Okay. What is that? It's going to be 4/3. Okay. And then how is that? It's going to be in series with the 4. So the overall I total is how much? It's going to be 16 divided by the total resistance of 4 plus 4/3, right? And once you find that I total, in order to find the I coming from the 16 volts, I have to use the current divider equation, right? And say that it's being divided between, oh, I have to say it's a minus, right? Because it's opposite the I total. It's going to be minus what? We're interested in the current in the 4, right? So it's going to be 1/4 divided by, what am I doing here? 1/4 divided by 1/4 plus 1/2 multiplied by the total current of whatever this is, 16 over 4 plus 4/3. Then add the 3 I's that I got will be my final I. Okay? So again, superposition, it's a nice idea, but it doesn't always necessarily simplify your solution. Okay. It's not hard, it's just tedious. You have to solve the problem 3 times. On the 2 amps. Okay, so when the 2 amp is on is when okay. Okay, so let's do the 2 amps. So this is on, and this one is replaced with the wire, right? Now, do you agree that this is one node, and this is another node, yes? And therefore, the 2 and the 4 are in parallel, because they're connected to, so if I erase it here and put the 4 here, it might be slightly clearer. So the 2 and the 4 are in parallel, you agree? That's how we got the 4/3. And when we got the 4/3, okay, the 4/3 is actually in series with the 3 then, right? Okay, so I added the 3 and the 4/3 to give you the 13/3. Why is it 13? It's 9 over 3 is the 3 plus 4/3 become 13/3. Yes? and then the 13/3 now is in parallel with the 1, then we apply the current divider equation. It becomes like this. Here's the 1,
4/3 plus the 3.
is the 13/3, which is now this. And you notice that it's now in parallel with the 1, and we apply the current divider again. Okay? But some of you, if you don't like current divider, you just want to use a mesh over and over again, more power to you. Okay?
How much do we have to simplify so we can be happy?
Oh no, if it's source transformation,
Oh,
that's the time that you need to simplify to make me happy, right? But if it's superposition, you can solve the resulting circuit any way you want. Okay? Do you see the difference?
yeah.
You do the transformation with the objective of simplifying it. But in doing the superposition, you're illustrating that you can find the individual contributions of all of the independent sources and then just add them, you get the final answer to be the same. However you solve each individual circuit, each individual contribution, it's up to you. Okay. Any other questions on the homework? Maybe we should continue with.
So we did all 3 of those to solve the I.
So we have 3 I's now. One from each of the 3 independent sources. You just add them algebraically now. That will be the total I. That will be the solution. Okay? No? Okay. It's algebraically, because this one here is actually positive. The contribution coming from the 20 volt is downward. The contribution coming from the 2 amp is downward. The contribution coming from the 16 volts is actually upward. That's why I put a negative here. So add them with their signs. Would be the net current. So, okay. Do you understand the general principle behind superposition? Okay, we have 3 independent sources. What we do is oh, you got the answer and you're okay now? Do I have the answer? It's in the book probably. But the idea is what? You have a circuit with 2 or more independent sources. What do? Find the contribution of each independent source, all the others turned off, and then add them. We need to finish Thevenin and Norton today and start on op amps because your op amp lab's gonna start on Wednesday, right? So let's finish chapter 4. Okay. Oh yeah, we were looking at this case. Just to refresh your mind, you probably forgot about this because of the test. Okay, we have this very powerful theorem that allows us to replace any complicated system of voltage sources, current sources, and resistors as seen by a load RL to be equivalent to a single voltage source V Thevenin connected in series with a single resistor R Thevenin. So the general idea, hopefully you understand the power of this theorem, is that it doesn't matter how many millions and hundreds of millions and billions of elements I have inside this box. As seen by the terminals of a load, I can always simplify all those elements into a simple combination of one voltage source and one resistor. And the voltage source is just equal to the open circuit voltage at the terminal. So basically what you do is what? Yank out the load and replace it with an open circuit. Whatever the voltage is across that open circuit is going to be your V Thevenin. And the R Thevenin is the equivalent resistance seen by the terminals of the load with all of the independent sources in the original circuit turned off. And how do you turn off How do you turn off independent sources again? If it's a voltage source, you replace it with a short. And if it's a current source, it's an open. Okay? So we looked at several examples, like this one here. To find R Thevenin, we replaced the voltage source with a short and the current source with an open, and then we found the equivalent resistance as seen by terminals A, B. And to find the V Thevenin, we yanked up the load, replace it in an open circuit, and compute the voltage across that open circuit. Then we found V Thevenin. No. So we're trying to see, okay, inside this, did you understand what I saw before this? So this is the load, okay? With respect to the terminals of the load, anything inside this box can be replaced by just one resistor and one voltage source. Okay? That's the whole idea. And what is the resistor? It says just turn off all the independent sources. So if you turn off all the independent sources and they're nothing but independent sources, you will see nothing but resistors. Okay? Therefore, you should be able to simplify all those resistors into one by using series parallel, maybe Y delta, if you're unlucky. That's R Thevenin. Okay? Now, the V Thevenin is the open circuit voltage across the terminal. So imagine taking out this load and replacing it with an open circuit and measuring the voltage across those wires, across those two terminals. That will be the open circuit. Okay, so I took out the RL. See this picture here? That's exactly the same as the original circuit. The original is the one that I didn't draw. Okay? It's on my left, so I don't know what you're talking about. The one on the right is what we're looking for.
Oh, that's what we're trying to get.
That's what we're trying to get. Okay? And there's someone with a raised hand. Yes, Carl. Where'd you get that 96 3V Thevenin? What is he talking about?
96 right on the bottom before you get the answer.
Oh, I multiplied everything by the LCD. What's the LCD of this? It's 12. Hopefully 12 times 30. Oh yeah, 3 times 90. Yeah, so 3 times 32 is 96. Okay, but going back to your question, Nihad, do you see that this circuit here is exactly the same circuit as the one that's written in the problem, except I took out the load, which is this, and replaced it with two dangling open wires. Okay? And whatever the voltage is across those two dangling terminals will be the V Thevenin. Okay? And you can use any method you want to find that V Thevenin. Okay? And the method we used nodal. Okay? The fact that this is open means that the current here is 0. Yes? If this current is 0, the voltage across that 1 ohm is also 0. So there's no voltage drop across the 1 ohm, yes, because there's no current. Why is there no current? Because it's open. Okay, so if there's no voltage drop across the 1 ohm, the node voltage on the left should be exactly the same as the node voltage on the right. So this is also V Thevenin. And that's what made me decide to use nodal, because there's only one unknown node. Okay, so I applied nodal, 32 minus V Thevenin over 4. You understand where I got this equation, right? Yes, it's the nodal equation. Okay, and plus 2. And take note, nothing from this branch, right? Because there's no current there anyway. So there's only 3 terms. Okay, equals 0, and then we solve for V Thevenin. So whatever this V Thevenin is, okay, is the voltage source we need here to be connected to the 4 ohms. How did I find the 4 ohms? I turned off all the independent sources. I shorted this, and I opened this. See that? Short, open. And then I simplified all the resistors I see. 4 and 12 are in parallel. Yes? No, they're in parallel. It's relative to this. Do you agree that I can move this here? Right? Because there's nothing there. No, they're not in series. Remember series, they have to be holding hands just by the two of them. Right? This 4 and the 2 are not holding hands, but there's another guy here. It's a threesome. Right? It's not monogamous, right? Right? Okay?
I thought maybe the 12 was where the wire was.
If the 12 was over here, yes. They're holding hands over here just by the two of them. Okay? But they are in parallel, right? Because they are connected to the same two nodes. Here's one node, which by the way is this entire thing is one node. And this node, that's why they're in parallel. Okay. Okay. So you get the general idea, right? We were able to simplify it by finding R Thevenin. It's just the resistance you see if you turn off all the independent sources. And the V Thevenin is just the voltage you see if you yank out the load and leave it with dangling terminals. Okay? However, what happens if you have dependent sources? Okay? If you look at this previous example, after we turned off all the independent sources, you are left with nothing but resistors. Right? And if we have nothing but resistors, we can definitely simplify all those resistors into one by series parallel or maybe Y delta if we need to. Okay. However, what happens if you have a dependent source? And according to superposition, we cannot turn off dependent sources. Only independent sources that we can turn off. So we have to leave the dependent sources. So the problem now is, how do we find R Thevenin? Okay, according to our result, R Thevenin is the equivalent resistance at the terminals after you've turned off all the independent sources. So only the independent sources, only the circles are gone. The diamonds will still be there. Right? So you're going to have a system of diamonds, okay, scattered around resistors. And we really have no way of simplifying that into a single resistor. Do you agree? Okay? So what do we do now? According to this, to find R Thevenin, we still have to turn up all the independent sources. Okay, but even after you do that, you're still going to have the diamonds. Okay, in order to find R Thevenin, you can do either one of these two. You can either apply a test voltage source of value V0, okay, and find the resulting I0. Or if you want, you can apply a test current source of value I0 and find the corresponding V0, and then divide the V0 by the I0 will be the R Thevenin. Okay, so why does this make sense? Well, we know that here's the original circuit, okay, and we know that this is our load. The load was over here, supposedly, right? And then as seen by the load, okay, this is supposed to be equivalent to just one V Thevenin in series with one R Thevenin. Are we okay with that? As seen by the same load. Yes? The two should be equivalent regardless of what load we apply. Okay. Now, according to Mr. Thevenin, okay, if I turn off all the independent sources, okay, what's going to happen? This is an independent source, right? So this is going to go away. It will become a short, right? If I turn off all the independent sources on the left side, okay? And according to Mr. Thevenin, after I do that, this whole box should be equivalent to just a single resistor. The problem is, if we have dependent sources, in addition to resistors here, we will have diamonds. And we have other resistors and maybe other diamonds, right? But according to Mr. Thevenin, there should be one resistor representing all those combination of resistors plus all the diamonds in it. Okay? Now, what we're trying to say is, if this is indeed true, and I look at the picture on the right rather than the left, and let's say I apply a voltage source here, a test voltage source of value V0, okay? That voltage source will supply power to the R Thevenin, right? Which means that it will develop a current I0. Okay? And if indeed Mr. Thevenin is not lying, if you look at the right picture, the value of R Thevenin must be equal to V0 over I0. Do you agree? Okay. The problem is we don't know what R Thevenin is on the right side, because there's no way to find. If I apply a V0, I cannot solve for I0 if I don't know R Thevenin in the right picture, right? So let's say we are applying this. I apply a test voltage source V0. I know it's supposed to develop an I0, but I will not be able to find I0 in the right diagram because I don't know what R Thevenin is. That's exactly what I'm looking for. Yes? However, on the left side, if I do exactly the same thing, meaning, okay, I'm going to apply a test voltage source here, V0, the same thing should happen, an I0 should develop, right? However, on the left side now, I should be able to solve for this I0. Why? Because the rest of the elements here are actually given in the original circuit. So I'm going to use the left diagram in order to find I0. And once I find I0, I look at the right diagram. Oh yeah, if I know I0 and V0, R Thevenin is just the ratio between V0 and I0. Clear? Okay, it's the same thing. Instead of applying for V0, if I apply a test current I0, the picture will tell me what? Here's my I0. Okay. And if Mr. Thevenin was not lying, remember this is now shorted, okay, because I turned off all the independent sources. If he's not lying, okay, as a result of my I0, I will develop a voltage across it equal to what? I0 times R Thevenin. And the same thing should happen on the left side. So if I solve for V0, that result from me applying the I0 on the left side here, I apply the I0, it should develop V0. And that V0 I should be able to solve. Why? Because I know everything that's inside the box. I solve for the I0 in the left diagram and look at the right diagram and say, oh, once I find V0 given I0, I'll find R Thevenin as V0 over I0. Clear? Now, we're going to make this even simpler because the value of V0, the test voltage source that I apply, okay, is really immaterial. Right? Whatever V0, if I apply one volt source, okay, it will develop a certain current. But the relationship between the left diagram and the right diagram should still be the same regardless of the actual value of V0 that I do. So what I'm going to do most of the time is I make my test voltage simple by applying, say, 1 volt all the time. We cannot use 0 though. Okay? So let's look at how to apply this here. It says here, it's easier to use test voltage of test current value of 1. So that's what I will do whenever I'm doing this problem. Okay, so let's look at this problem. Find the Thevenin equivalent circuit. So finding V Thevenin is not a problem. Okay, what is V Thevenin? It's the open circuit voltage that results after I yank out the load. It looks like I already removed the load, right? The load's not shown here. So this is now open circuit, right? If I label this as plus and this as minus, okay, the voltage across this will be my V Thevenin, which is the voltage open circuit. Okay? Are we okay? So this voltage here, whatever that voltage is my V Thevenin. Now, again, I observe that, okay, the current here is how much? Is 0, right? Because 2 ohm is connected to an open circuit. Therefore, what's the voltage across the 2 ohm? 0. Okay, so if I intend to use nodal analysis, okay, and call this my reference, okay, what's the node voltage here? That's too many zeros here. What's the node voltage here? V Thevenin, right? And what's the node voltage here? It's also V Thevenin, right? Because the voltage across the 2 ohm is 0. Why? Because the current through it is 0. Now what is the voltage, node voltage here? Here. What's the node voltage here? Because I'm setting this up for it's Vx. I'm setting this up for nodal analysis. I'm trying to label all non-reference nodes. So I think I'm ready for nodal, right? And do I need a super node for this one when I do nodal? Yes, right? Because of the voltage source here between Vx and V Thevenin. So I'm actually going to need the nodal analysis, nodal equation for supernode that combines Vx and V Thevenin, right? Okay, so I imagine having this shell around here, right? And applying nodal for that shell, okay? First term, positive 5. Second term, 0 minus Vx divided by 4. Third term, whoops, no. You only look at contributions of currents entering your shell. The 2 ohms is completely inside your shell, right? You don't account for that. So we only have one term left. 0 minus V Thevenin divided by 6. Anything else? No, because that 2 ohm doesn't have a current. Okay? Okay, that's my first equation. Now I lost one of my nodal equations because of the voltage source, right? So the voltage source better give me my extra equation. And how do we solve for that extra equation? By, what do we call that? By inspection, rather than by KVL, like the book wants you to. So by inspection, which one is higher, V Thevenin or Vx? By how much? Okay, so what's our equation? V Thevenin is higher than Vx by 2Vx, which means that V Thevenin is equal to 3Vx, right? I will substitute that. Oops. Let me solve for V Thevenin first because I don't like fractions of Vx first. So I'm going to substitute this into this. I need your help. So let's multiply everything by the LCD, which is 12, right? So it's going to become 60 for the first term. The second term will be how much? Oh, no. The LCD it's just 4, right? Because this is replaced by 3Vx, right? Do you understand? I want to simplify it. Because this guy here becomes what? Minus 3Vx. Yes? I will cancel the 3 and the 6, so LCD is actually just 4, yes? Do you agree with me? So it's going to be 20 minus Vx, right? Minus, how much? I think it's 2Vx. Right? Is that okay? Okay. Equals 0, so, oh, that's not a nice number. So Vx is, what? 20 over 3. Don't worry about the 3 in the denominator because V Thevenin is 3 times that, so V Thevenin is 20 volts. Okay? Do we have an answer? We don't have an answer. Okay? So are we okay with how I found the V Thevenin? Now I need to find R Thevenin. Oops. How do I find R Thevenin? How do I find R Thevenin? But we don't know. V naught, we don't know I naught. So how do I... Okay, we need to turn off... First thing you do is turn off all the independent sources. Okay? So 5A's got to go and be replaced by... What? Oh, no. No. it's a current source. You need to... Okay. I appreciate your being nice, but you're wrong. And you don't get extra credit for being nice. Okay. So I replace my current source with an open circuit, right? And I'm redrawing the circuit now. This is my 4. Okay, this is my 2. This is my minus plus dependent source 2Vx. Okay, and then I have this, and then I have my 6. Everyone okay with my new circuit that I obtained by removing the current source? And this would still be my Vx. By the way, okay, here's a very common mistake. The value of the Vx here, when we were solving for V Thevenin, is not the same as the value of the Vx when we were solving for R Thevenin. You agree with me? Because those are completely different circuits. When we were solving for V Thevenin, we did not turn off anything, yes? When we were solving for R Thevenin, we turned off the 5 amp source, okay? So don't be lazy by saying, oh, I already have the Vx, therefore this Vx is 20/3. That's wrong, okay? So what do we do now? So according to Mr. Thevenin, okay, this whole thing here, as seen by the terminals of the load AB, okay, should be equivalent to a single resistor. And here's the problem. We don't know how to simplify that resistor because it has a diamond in it. If there was no diamond in it, it would have been easy, just series parallel. Okay? That's why we're devoting this time into analyzing Thevenin equivalent circuits with dependent sources, because it's a different story. So what do we do, according to what we said earlier? Yes, it says here, according to Thevenin, this is equivalent to a single resistor, R Thevenin, right? Okay, but we don't know what R Thevenin is, but according to Mr. Thevenin, one way to find this is by what? Applying a test voltage source, okay, in the terminals, or a test current source. Which one do you want to try? Voltage or current? Okay. You want current? He said current, so let's do current. So I'm going to apply a test current source here. I'm going to call that I test. Of value, okay, 1 amp. Okay, and as a result of that I test, let me move that somewhere else. This is my I test. Okay, as a result of that current, okay, a voltage will develop across the current source, and that's what we're calling V test. And okay, yeah, because what we're doing is really, we know that it's equivalent to a single resistor. So if you look at the right side of the equation, if I apply a current source here, that will develop a voltage across it. and the voltage divided by the current I apply will be numerically equal to R Thevenin. That's basically what we're doing. If indeed, does that make sense? If indeed all the dark, the black diagram here is equivalent to the black diagram here, which is just one resistor, whatever I do on the left diagram will be exactly what I'm going to do on the right side. And if you look at the right side, if I apply a current source, that will develop a voltage across the current source, and the ratio between that voltage and the current will be numerically equal to R Thevenin. Do you agree with this?
We start off with the image on the right side saying we're going to put this 10
yes.
and then we know R Thevenin.
We don't, that's the thing, we don't know R Thevenin.
The black diagram that says
correct.
facing as the left side with the black diagram.
Correct.
Now we try and find
So we're going to use the left diagram to find V test.
V-test and an I-test.
The I-test I just applied arbitrarily to be 1. Okay? But because of that I-test, I will be able to find a V-test here. Once I find V-test, I look at the diagram on the right side. The ratio between V-test and I-test is actually R Thevenin.
So we say I-test is going to be 1.
And then solve for V-test.
And then always do V-test.
No, you can also apply a V-test and solve for I-test. But he said he wanted, let's do both and see which one's better, okay? Okay, so our objective now is to find V-test. Because, so I'm going to call this voltage VA. That's not V Thevenin anymore. And this voltage here is Vx. Yes? Then I'm going to apply, do you want to do nodal again since we are in a nodal mode? So, but it's going to be a supernode again, right? The supernode equation will tell me 0 minus Vx divided by 4, right? Plus 0 minus VA divided by 6. Are you okay with that? What else? Plus 1 equals 0. Is everyone okay with how I'm getting that? Here's my supernode. And do you agree that the current entering it is 1 amp? Right? So I use the 1 amp rather than invoking V test minus VA divided by. Okay? Hmm? The whole thing is a supernode. I could have called it V test minus. Do you want me to call this V test minus VA divided by what? By what's that? 2. It's the current source. Do you agree that the current coming from the current source is 1? Yes? And nodal is really just a KCL. Now, some of you, instead of calling it 1, would have called it what? V test minus VA divided by 2, yes? You agree? And that would have been perfect too. That would have been correct also. Yes? But I like the 1 better because it doesn't have an additional unknown at this point. So do you understand where I'm getting the 1? The current coming from the source, the test current source, is actually gonna go through the 2 ohm, will enter my supernode. That's still 1. Okay. Now, what do I have now? I have 2 unknowns, Vx and Va, because I lost one of my nodal equations, but worry not, because we're going to have another equation. Va minus Vx is again equal to what? 2Vx, so that Va is equal to 3Vx. So if I substitute that here, so let's simplify. So my LCD is again just a 4, right? So I'm going to get, the first term is going to be minus Vx, right? The second term will be minus 2 Vx. Am I doing this correctly? You have to watch my algebra. What will be the last term? Plus 4 equals 0. Yes? Which means, yes? Anybody with a complaint? The 4 came from 1 times the LCD. The LCD was 4. So I'm going to get a Vx that is 4 over 3. Okay? But that means that the VA is 4 volts. Okay? Are we really solving for VA? What are we solving for? V test. Okay? So how do I find V test now?
The one that
Okay, V test minus VA divided by 2 equals 1 amp. Yes? The current through the 2 ohm is the difference between the node voltages of the 2 ohms, right? Divided by. So what's our V test now? V test will be 2 plus VA, which is going to be 6 volts, right? Okay. So what is our R Thevenin now? You're really trying. It's going to be the V test divided by the I test. That we selected I test to be 1, so R Thevenin will just be 6 ohms. Hopefully that's correct. Okay? Oops. Okay? That looks like a 650. It's really ohms. Now, we used an I test of 1 amp only because somebody suggested it. Okay, we could have used in finding R Thevenin. Let's try and use. So I'm going to find R Thevenin again, but this time I'm going to use a V test of 1 volt. Okay, so I'm going to redraw the circuit again with the independent sources turned off. So it's going to be exactly like that black circuit on the right there. So it's going to be what? Help me here. 4 ohms here, right? Dangling open terminals coming from the current source. And I think this is the Vx, right? And then we have 2 and 2 Vx. This is 2 ohms here. And here's our dependent source. Minus on the left, plus on the right. And it's a value 2 Vx, right? And then, what am I missing? 6 and 2. 6 here. And 2 here. Okay? I think that's correct now. These are my terminals A, B. Okay, and so I'm redoing the part of trying to do R Thevenin by applying a V test now. So I'm going to apply a V test. Okay, so it's a voltage source now. V test of value. The value doesn't matter, so make it simple. Here's 1 volt. And as a result of applying that 1 volt source, is indeed everything on the left side of AB is just a resistor. Okay, that voltage source will develop a current through it called I test. Okay. Now our objective is to find that I test, because if we divide 1 by that I test, it should be equal to R Thevenin. Okay. So what do we do? Well, since we've been using nodal, let's continue with nodal. Okay. So I'm gonna. This node voltage here is Vx, right? This node voltage here, I'm going to call it VA again, but this VA is not necessarily the same as the VA before, right? Because this time I have a 1 volt test source. Previously I had a 1 amp test source. Okay? So let's do our supernode again. It's going to say that 0 minus Vx divided by 4, right? Plus That's what? 0 minus VA divided by 6 plus, what's my third term? What's my third term? Okay, V test, which is 1 volt, minus VA divided by, what is that resistor? Okay, let's replace it with it. Everyone okay with how I got this nodal? This time, instead of calling it I test, which I could have, right? I used 1 minus VA divided by 2 because I don't want to introduce an additional unknown. I'm reserving finding I test at the end once I already have all the node voltages. Correct.
So, I guess this case, you use V test as 1V and then I test as 1, right?
I want to say yes, but I didn't understand what you said.
We had more unknown.
Correct. So you want to use things that you know rather than using something that's unknown. You want to minimize the number of unknowns. Okay? Exactly. Okay. So LCD is, oh no, what do we do next? Supernode, then we lost one of our nodal equations, but we still have that VA is higher than Vx by 2Vx, so we still have the same exact relationship we've been using for the third time now. Okay, substitute that to the VA, so my LCD is still 4. That's good. So the first term will be minus Vx, the second term will be minus 2Vx. You really need to watch what I'm doing here, okay? And then the third term will be 2. Did I do that correctly? And the fourth term will be minus 6 Vx. Okay, equals 0. Combine all the Vx's. What do we have? 1 plus 2. 9 is 2 over 9. Vx is equal to 2 over 9. Okay. But is it really Vx we're solving for? No, we're solving for I test, right? So what is I test? I test is also the current to the 2 ohms, which is node voltage on the left, which is 1, on the right, which is 1, minus node voltage on the right, which is VA, right? Divided by 2, yes? I think I messed up my left and right. So this is going to be what? 1 minus, what's VA? 2/3, right? Yes, why is it 2/3? It's 3 times 2/9. Yes, divided by 2. So what is it? 1 minus 2/3 is 1/3. Divided by 2 is 1/6, right? Okay, so once I find I test, what is our R Thevenin? It's V test over I test, right? What's our V test? 1 volt. What's our I test? 1/6 amp. So what's our R Thevenin? And is that exactly the same as the previous one? Okay, so the question is, which one do you think is simpler? Was the current simpler? Huh?
In this case, deciding V test 0 volt.
He doesn't agree with you.
You chose to make I test 1.
On the first one,
yeah.
I test was 1. On the second one, V test was 1.
Right.
Which one's simpler? You're saying that this one is simpler. Okay. In fact, why did we use nodal? We could have used mesh. Maybe it was simpler. So how do you know it was simpler? We have 3 meshes, right? If you're going to use mesh, this is probably better, because at least your third mesh is known. minus 1 amp. So you only have 2 unknowns. If you're going to use this and use mesh, this is probably more complicated because you have 3 unknown meshes. Do we? You have 3 meshes here, right? Let's assume that I'm going to use V-test, but instead of using nodal, I use mesh. This is not good, right? Because I have 3 unknown meshes. But I use node. Okay, so if I decided to use V-test, I would probably use node. Right? But over here, if I've applied a 1 amp, I think mesh might be slightly simpler than nodal. Do you agree? Because I don't need a super mesh, and my third mesh is actually known. So I only have 2 unknowns. The third mesh is the one on this side. Because it's 1, because of the 1 amp, the I3 will be minus 1. Yes. Oh yes, very good. You could have done transformation also. So I could have transformed this into oh no, you can't. This one here?
No, the one where you put the voltage.
Excuse me. This one yes, I can do source transformation here, but I have to make sure that I don't lose anything. Okay? Because this is kind of dangerous. Because if I combine the 2 and the V-test into a single current source in parallel with the 2, now I have 2 currents. One through the 2 ohms and one through the current source. So which I am I looking for?
Would be V-test type.
And do you understand? If I transform this, I will actually lose I test. Because if I transform that, it becomes like this, right? It becomes a 2 ohm resistor in parallel with this, right? This is, what's the value of this now? It's 1 times 2. 1 divided by 2. So 1/2 amp. So where's my I test now? This is my I test, right? Because I test is what enters the VA. So this is not my I test here. So you have to be careful when you do that. But you agree, this is the I test that I need in my process. Anyway, but do you understand the general idea, right? For node, oh, well, now I'm in trouble. I told your lab teacher we're going to start op amps today. Okay, so let's at least finish Norton. Okay. Not like, oh, I shouldn't say, it's being recorded. I caught myself there. Okay, Norton's theorem, okay? It's, in my opinion, kind of a cheap theorem. It's a corollary of, or to, either one's fine, to the Thevenin's theorem. Okay, what this says is as follows. Instead of, so same thing, you have a system of elements, any number of voltage sources, any number of current sources, any number of resistors, okay, in this complicated box, as seen by the terminals of the load AB, okay, according to Mr. Norton, okay, you can always replace it by the parallel combination of I Norton and R Norton. And how do you find R Norton? R Norton is really just the same as the R Thevenin before, okay? And of course, IN is equal to V Thevenin over R Thevenin, but you can actually solve for, according to Mr. Norton, okay, the I Norton is equivalent to the I short circuit, which makes sense, because if I replace the load with a short circuit, okay, what's going to happen to the I Norton? The entire current coming from the I Norton would rather go through the short circuit rather than the RN. So the short circuit current will be equal to the I Norton. So what I was saying is it was kind of cheap because if you recognize this, okay, it's really just a combination of Thevenin plus source transformation. Because according to Thevenin, what does Thevenin say? According to Mr. Thevenin, the left side is equivalent to a V Thevenin in series with an R Thevenin as seen by the terminals AB. Oops, AB, right? And we also know that source transformation allows us to transform that voltage source in series with a resistor into a current source in parallel with the same resistor. It's kind of cheap, you know. It's like he puts the Thevenin and source transformation together, and now you have. Although he did suggest that I Norton can be determined directly by finding short circuit. So some students would solve for I Norton using this, and I guess that's fine. But you can actually find I Norton by finding the short circuit. It's not an I Thevenin. It's I Norton. Because Thevenin didn't do it. I don't know I'm not an electrical. Okay, so the Norton equivalent circuit is very similar to Thevenin, right? Except now you replace the original circuit with a single current source I Norton in parallel with R Norton, which is of course this R Thevenin. So the way you find R Norton is the same as the same way you find R Thevenin. Turn off all the independent sources, find all the resulting equivalent resistance as seen by the terminals of the load. Again, depending on whether you have independent sources only or dependent sources in your system, you might need to do V-test or I-test. Okay? And if you want to find I Norton directly, it's equal to the short circuit current through the terminals. Okay. Let's do a very quick example. So find R Norton find the Norton equivalent circuit. So quickly, what's our I Norton? R Norton. So we open this, right? And we short this, right? So what do we get? R Norton will be the 8 in series with the 4, in series the other 8, in parallel with the 5. Yes? Are you okay with that? Yes or no? Yes? Okay, and that's going to be 20 parallel to the 5, which is 4 ohms. Everyone okay with how remember, it's relative to this. So it looks like this, and the 8 here, and the other 8, they're all in series, right? They are in series, and then never give up. Some students will say, aren't they all just in series? Well, no, because you don't need to give this up. It's a threesome here, okay, as seen by A and B. Okay. Now, so how do you? Now, Nihad is interested. Okay. How do we find I Norton? We can find V Thevenin like we did before and divide V Thevenin by R Thevenin, but I think that's kind of cheating. I Norton is the I short circuit, okay, which means that I short the terminals of the load, replace the load with a short circuit, and whatever current develops there is the I Norton. Okay, so any suggestions on how I find I short circuit? No, there's no testing in here. The testing only is for finding R Thevenin, and there happens to be a dependent source, right? There's no dependent source here. So how do I find I Norton? So what can I say about this 5? It's gone, right? It gets disconnected. Are you okay with that? When a resistor is parallel to a short, that resistor will never get any current. Okay? So what's the quickest way of finding the... Why is it gone? we shorted this. Okay? So if I have a current trying to divide itself into a 5 in the short, what would the current do? It will just go entirely through the short. Nothing is going to go through the 5 ohms. Yes, or another way of looking at it is, what is 5 parallel to a 0? Short circuit is really 0, right? What is a 5 parallel to a 0, Ben? Use Ben's equation, it will be 0, right? If it's 0, it just appears as if the 5 is not even there, right? Okay? Now, what is the quickest way of finding I short circuit? Mesh, right? Mesh, right? I think mesh is, there's only one unknown mesh, and that unknown mesh is the I short circuit we're looking for. This is 2, right? Do you agree? This is, what's the mesh here? I short circuit. Because if you do source transformation, you're going to have to do it like 2 times at least. Change this, absorb the current source, and change that, right? Here, I only have one mesh equation, because the mesh on the left is actually defined. So the mesh equation will give you minus 12 plus 4 times I short circuit that I'm looking for, minus 2, right? Plus 8 times I short circuit, okay? Plus another 8 times I short circuit equals 0. So what is that? Minus 12 minus 8 plus 4 plus 8 plus 8, what's that? 20? So it looks like I Norton, which is the same as I short circuit, is just 1 amp. Okay? That means that the original circuit is equivalent to a 1 amp source in parallel with a 4 ohm resistor. This is your I Norton. This is your R Norton, which is also your R Thevenin. Okay? Are we done here? Oh, maximum power transfer. I'm really in trouble. Okay. We'll do this quickly next time. If he asks you before your lab if you've done op amp, your answer is yes. Because we're going to do the op amp on Wednesday. No, your lab that's due today is Thevenin and Norton. Oh, I mean on Wednesday. So that's not op amp. You were supposed to know that like last week, right? Okay. Bye, Carl. I will kill you, Carl.
Bye, Carl.
Oh.